Thanks a lot for the opportunity to speak here. So I will talk about this sort of a theme, partial randomization for better approximation. And first I'll say very briefly something about randomness in certain tasks in approximation in quantum computing. And then I'll discuss two applications which are similar in spirit but not very directly related. So okay, so a general principle for quantum computing, I think very important general principle, is that coherence is better than randomness, right? That's what the whole endeavor of quantum computing is based on. And for example, if I have some state, then and I have like a good part and a bad part, then instead of just measuring and hoping that I get the good outcome, what I should really do is amplitude amplification, and I'm faster, right? So randomness is not good in quantum mechanics, in quantum computing. But as this workshop is about information processing with limited resources in the near term, there are actually quite a lot of cases where randomness helps you. So this is, for example, in error mitigation, where randomness can help you, to get rid of some of the noise. In randomized compilation, where compilation to T-gates can help you, randomization can help you. In Hamiltonian simulation, that's an example that I'll cover later. Also in examples where you don't have a trusted device, randomness can help you to sort of not get tricked. Or we actually, before the break, we saw a nice example with randomized benchmarking and other applications in benchmarking where randomness is really key to overcome certain limited resources. So this was a very generic statement. And now I want to talk about a specific instance of this, or a slightly more specific instance, which is still about a simple principle. So suppose that we have some target state, psi, which we want to approximate, and we have some states available through maybe a limited gate set or some limited algorithm or whatever. And they approximate this, and let's say that they have fidelity 1 minus epsilon with the target states. So then I drew this picture here on a sort of block sphere where they approximate the state psi, but often in this case, if they're sort of like equally far away on both sides, then actually if I take their mixture, then just from this simple geometric argument that you see here, the mixed state that is sort of like half the one, half the other one, is now within trace distance epsilon from the target states. Okay, whereas sort of like the trace distance between psi and each of the phi i's was square root epsilon. So a lesson from this picture is that mixed states can be better approximations than pure states, but also in this picture, sort of the catch is that this is the case if I measure with respect to trace distance and not when I measure with respect to fidelity. It's not hard to see that if I just compute the fidelity of this mixture with the target state, then it actually doesn't help me. But for the trace distance, sort of because of this picture sketched here, I do get an improvement. Okay. So we're going to apply this principle to a concrete problem, which is about truncating quantum states. And here we assume that we're given some pure quantum states, psi, and it lives on a Hilbert space of dimension d. And what we want to do is we want to approximate with a k-sparse state, meaning that it only has k non-zero coefficients. Or a similar problem is we have a bipartite state, and we want to approximate, right? It has a Schmidt decomposition in principle of d terms, but we want to approximate it with a state which only has Schmidt rank k, so with bounded entanglements. So I will focus on the first problem, but it's like all of the results that all the things that I will mention are, carry over directly to this second case as well. Okay, so question to the audience: what is the best approximation that we can make? Let's say for this first case. Anyone knows the answer? Yeah, excellent. So, the answer is, we keep the largest k coefficient. So that was immediately insights from the audience. So it's a very easy problem. But it turns out that this is the right answer only if you care about the fidelity. And if we want to measure distance by trace distance, then for pure states, what we know is that the fidelity squared plus the trace distance squared is 1. So if the fidelity is, let's parameterize it as square root 1 minus epsilon, then the trace distance is square root epsilon. And on the other hand, the Freek van der Graaf inequalities in general, they would, in this setting, bound the trace distance between epsilon and square root epsilon. So in some sense, the pure states are really at the very bad end of the Freek van der Graaf inequality. And the question is, so as I explained before, you can actually do better if you allow mixed approximations. And then, of course, you should really ask in this whole business, which distance measure do you actually care about? If it is the fidelity that you care about, then you should not go with these randomized approximations. But in some cases, maybe you care more about the trace distance. So if you care about expectation values to additive precision of some fixed observable, then maybe the trace distance is the more relevant operational quantity. So we've studied this in a joint work with Aram Harrow and Angus Lowe. And, it should be on the arXiv on Friday, as maybe more works presented here. And, let me go. So it's best understood by going to an example, simple example, but this fully shows what happens. So suppose that we have a state which is like mostly 0, and then a little bit 1 and 2, and we want to approximate it with a state which only has 2 non-zero coefficients. And then it's clear what we have to do, as was suggested by Riwai. We have to just, pick either of these states where we take the 0 state and, one of the 1 or 2 states, like either is equally good, and that's it. Now, if we look at the density matrix of the state that we are targeting, then what we see is that there's obviously a dominant term in this density matrix on the top left. But then the next largest terms are these sort of like off-diagonal terms, which are order square root epsilon, and that's sort of the order square root epsilon that we're getting in the trace distance error when we approximate by one of these states, right? Then we're always going to miss one of these next largest entries. So however, if you take the mixture of these two options, then we see that we can actually sort of cancel all of these red entries here, and we're left with a trace distance error which is order epsilon. Okay, so that means that the best approximation in trace distance here is with probability 1/2 we take sort of like the one approximation, and with probability 1/2 we take the other approximation. Let's look at another even simpler example actually. So here we just have 0 and 1, and we want to, it's mostly on the weight is mostly on the 0 state, and we want to approximate it by just a single coefficient. And now, okay, it's obvious again what we have to do. We have to just pick the 0 state. But now it's also easy to see that actually there's no way to cancel these off-diagonal terms. We could sort of like with probability 1 minus epsilon pick the 0 state, with probability epsilon the 1 state, but it doesn't help us that much. So here the best trace distance error really is the one that is achieved by the pure state approximation. Okay, so we sort of look at this and we give a general result for this setting where we show how to exactly compute the optimal trace distance approximation if you are starting with some pure state and you fix the k that you allow. Then we show how to compute the optimal trace distance approximation to this state. And I want to emphasize that this follows up on some previous work. It's really quite closely related to Regula, Johnston, and their collaborators, where they also looked at this problem, but mostly for a different distance measure, which is the robustness, and also a special case of what we're doing here. But we give sort of this general characterization for the trace distance. And it turns out that the answer is pretty much as in this first example that I showed you, where if you look at the coefficients of the state, the amplitudes, then there's a bunch of them which are sort of like the largest ones, and you just keep them deterministically. Then there's a bunch of coefficients, maybe somewhere in the tail, that are very small, and you just discard all of them because they're so small. And then in between, there is a range where you're going to sample from. And it turns out that the optimal approximation is sampling from states which look like what I write here. So up to some weighting, we just keep the first k minus r terms, and then we pick a uniform superposition over r leftover terms from this middle region, and then we sample these according to a probability distribution that sort of is determined by the size of these weights here. So we have to make sure we sample these sets that we pick here such that they have the correct marginals to match the amplitudes here. And our second result is that we show how to actually do this sampling efficiently. So we give a completely efficient algorithm to compute this approximation and also to do all of the sampling. Just to one point to make clear, this is not that there's something subtle here, is that if you actually go to a different question where the state that you start with is already a mixed state, and I want to approximate it by a mixture of sparse states, then the approximation problem becomes NP-hard. And it's not so surprising if you think back of the variant with the entanglement. There we of course know, or there it's a well-known fact that for pure states, determining whether something is entangled is easy because it's just a Smith decomposition, whereas for mixed states, even determining whether a state is entangled or not immediately becomes NP-hard. Okay, so these are the results in this paper. And our main motivation and application of this, which we haven't worked out in great detail yet, is to tensor network truncation. So if you think about these two cases that I already mentioned, sort of like the K sparse and the K Schmidt rank, that really is very similar to having sort of these tiny tensor networks and trying to truncate their dimension in an optimal way. But you could also look at matrix product states where you want to sort of truncate these bond dimensions here to some fixed value K, and then you want to do that in a good way. And of course, the standard way to do this is sort of very similar as before. You have to do some singular value decompositions, and then you just keep the largest singular values. But in principle, here the same approach applies, where you could also choose which singular values you keep in a randomized way. And while there is no sort of like, if you want to look at the joint problem of all of them together, there's no, it's sort of a difficult problem to determine what's the optimal thing to do. But you can, of course, just do it bond by bond and apply the technique that we suggested. And then it seems like a good idea to use this optimal approximation in the bipartite case to this as well. And this truncation is a very important subroutine in tensor networks. Like often, bond dimensions grow and they have to be truncated again. And the dominant cost in these procedures is really, it scales with the bond dimension. So you have to truncate it, and making it smaller is a big deal for the cost of your method. So it may be worth to do a bit of sampling in order to get the bond dimension lower. And additionally, in many cases, we also actually do care about observables, like we want to compute the energy or local observables, so it makes sense to think about trace distance approximations. So for this reason, we think this is sort of a promising domain of application. And we also have some preliminary numerics. So here, again, I don't want to explain it too much, but we look at some random MPS, and we see that the relative error for the randomized approach that we use is sort of like very accurate. The variance isn't too bad, actually, and it overall seems to perform better than the deterministic variant. So we think this is a promising application, but it will be follow-up work to explore this in more detail and really see whether this is practically relevant. There's also previous work, let me mention it, by a very nice work by Ferris on this idea, but he uses a similar scheme, but he doesn't use this partial randomization, which we claim is optimal, but he sort of like samples from, he sort of does a scheme where the blue region is everything. So he samples from everything. And we hope that this makes this idea more practical. Okay. Then I want to go to the last part of the talk, which is about sort of this idea of partial randomization. Can also be applied to Hamiltonian simulation and product formulas. So, and by partial randomization in this previous part, I mean that we saw that the optimal thing to do was that there are some terms that we keep deterministically because they are large, so they're really dominant. But then there's also sort of like some smaller terms which it is best to sort of randomize over. Okay, so Hamiltonian simulation is, of course, a very important primitive where we have some Hamiltonian. Let's assume that it's a linear combination of Pauli operators. And what we want to implement the time evolution according to this Hamiltonian, but let's say that we can only, that we want to do this in terms of evolutions along the individual terms, which in this case are Pauli rotations, which can indeed be implemented efficiently. Then, of course, the standard solution that you could take is to use a product formula where for small times, this expansion is valid up to some error, and then for longer times, you just break up the time interval into R steps so that you have short times and this expansion is valid, and then you take care of things such that the error is small, and then you see that you have sort of decomposed this time evolution in these Pauli rotations up to some small error. So this is Trotterization. And if we look at how expensive this is, then the number of times we have to implement this gate, well, it clearly scales with L, the number of terms in the Hamiltonian, because we have to loop through all of them. And then it also depends on how many steps we need to break the time interval up to. And if you use a pth order method, then it sort of scales like this. So that's sort of a standard solution, a deterministic approach. It has a bunch of downsides. One thing, a big downside actually, is that it scales with the number of terms. And this number of terms could really be very large. In many chemistry examples, if you, in sort of unstructured examples, in principle, there are order n to the 4 terms, where n is the number of qubits. It's very large. The scaling with t is suboptimal. And actually here, I really did very hand-wavy things. And getting the error dependence is really quite subtle. And there's sort of like a whole bunch of constants here that are also system size dependent. And yeah, that's also a bit annoying. Okay, so an alternative is to actually randomize this. So random product formulas, the most well-known example is called QDrift. And here, what you do is really, well, first of all, I want to, in this Hamiltonian, I want to rescale by lambda the sum of the terms such that the coefficients in the Hamiltonian actually form a probability distribution. And then proposed by Campbell is this approach QDrift, where what you do is the following. Essentially, you take, again, a short time evolution, and we just do a Taylor expansion. So we have an order delta squared term, which is small because we're looking at small delta. And then for the first order term, we can group it together like this because it's a probability distribution. I can take this sum out of I can also group this first term inside. And now we see that we have identity plus I delta Pauli operator. And this together is actually proportional to a unitary, namely to, well, a Pauli rotation over some angle, which I guess happens to be it's over some angle here, doesn't really matter so much. And then we recognize that we have this unitary that we want, and it's over probability distribution, something proportional to a unitary up to some constant, and then an error term. So what we can do is we can just sample from the distribution and apply this unitary. You can actually also get all of the higher order terms, like this order delta squared. You can just keep going with the Taylor series, and then there's a paper that also explains how to get these higher order terms. And here, and what's also nice is that if you, in many applications, in particular, if you're using this inside of a Hadamard test for phase estimation, then what you care about is sort of only is something linear in the unitary. Okay, so that means that if we have sort of this expansion of the unitary as an expectation over something proportional to unitaries, then you can actually use it to get an unbiased estimate of the thing that you're trying to compute. So that makes the error analysis very easy. Okay, and then finally you can do the same thing as before with the trotterization, where we just divide up a longer time interval into many short time intervals. And then we just sample, we do the sampling process R times. Okay? Now, one crucial, so the reason why you have to break this up here is like, okay, you can think of this, it's maybe this order delta squared term, but another way to see this is that here, this is only sort of proportional to a unitary, and there's some normalization constant. And if you sort of like, to make sure that this normalization constant stays order 1, and doesn't sort of like give a very large sample overhead in this estimate here, you need to take a number of steps which scales as lambda squared t squared, where lambda was this normalization of the Hamiltonian and t is the time you want to simulate. So what we see is that actually if we look at these deterministic product formulas, they scale with the number of terms in Hamiltonian, which could be very large, and then some power of t. The randomized approaches, they kind of inevitably scale with t squared, which is worse, but they do not scale with L, but they scale with this lambda squared. So that is sort of not completely comparable. And sometimes the one thing is better, sometimes the other thing is better. And we have a sort of, we have a work on the arXiv with these people, most of the work done by Jakob, where we, do a sort of very detailed study of these methods in the context of chemistry and realistic chemistry Hamiltonians. And there, what these Hamiltonians look like if you look at the distribution of the terms, then there are sort of like, there are larger terms, and of course there are also smaller terms, and the total number of terms is very large, and typically there is a pretty long tail of very small terms, because we have these 1 over r decaying terms in the distance between electrons. So, and a very natural thing to do is also here to look at partially random product formulas. So this is something that was proposed a couple of times. We take a scheme by Hagen and Wiebe, and we modify it a little bit, and we do a different error analysis. And this has the same philosophy as what I mentioned before, where what you're going to do is you're going to try to sort of get the best of both worlds, and you, for the large terms in the Hamiltonian, they would contribute a lot to the normalization factor. So you'd rather, so you keep them in the deterministic parts, because they're maybe more efficiently implemented. But then there's sort of like a long tail with many small terms, and those you're going to implement in a randomized way. And then there's actually also, in this case, there's actually sort of like this order n to the 4 that I mentioned. Like that's really more than you need typically, and there are a lot of very small terms which are so small that you can just ignore them. So, so what you're going to do is you're going to take the Hamiltonian, and you're going to decompose it into a bunch of terms which you're going to treat deterministically, and this L prime hopefully is much smaller than the L that you started with, and then everything that you don't put in here, you keep in this remainder term, which you're going to do in a randomized way, which has some normalizing factor lambda r, which is going to show up in the costs. And then, in this case, we just numerically balance L prime and lambda r, so that the result is has sort of like the lowest possible costs from this. So it's a fairly heuristic approach. So the paper is very long and it has a lot of details which I don't want to go into. But what we do is we give sort of a simple error analysis, which is just which only involves really the trotterization error of this deterministic part. And then we make a sort of detailed numerical investigation. And our conclusion is mostly that if you sort of go from the fully deterministic scheme to this partially deterministic, partially randomized scheme, the trotterization error doesn't change so much when sort of grouping all of these small terms together in one randomized big term. So that's good. And then we make some resource estimates for molecular Hamiltonians, and we see that sometimes it's a little bit helpful, and sometimes it's not so helpful. So the example where it's most helpful for us is if you just take a chain of hydrogen atoms, where indeed you expect that there's sort of like a long tail of small terms, and then we see that if we compare the deterministic, the randomized, and the partially randomized gate counts for doing phase estimation for the ground state energy, then we sort of gain 1 order of magnitude of improvement. So that's useful, but in other examples it's not so useful. But I think that this is, and I think also one lesson to me from this project really was that we were interested in thinking about Hamiltonian simulation for relatively near-term applications, and these things in principle compete with better methods based on qubitization, probably familiar to many people here, and those methods are simply better, but they do require relatively complicated circuits and ancilla qubits and so on. But I think that still, if you look in the regime where things get classically difficult, it's still really, so with these product formulas, you could hope that they have simpler circuits, so maybe you can run them on more near-term devices, and I mean, you certainly can, but I think that the regime where you can compute things which are difficult for classical methods doesn't overlap very much with the regime where product formulas are cheaper than qubitization potentially. So I still think this is an interesting direction to explore, and then if you are exploring this direction, and I think this partial randomization, if you're looking at realistic systems, is actually quite useful. But it's also not completely convincing in my mind. Okay, that's all I have to say. Thanks.
Okay, do you have some questions? Thanks. Thanks for the great talk, Freek. How do you combine deterministic with randomized Hamiltonian simulation? Are you still doing some trotter type?
Yeah, right. So here, I didn't explain it very well, but the idea is actually very simple. So you can just, if you have this, you just do this deterministic expansion, but now we keep the part that we're going to deal with sort of randomly, we're going to keep it as sort of like one term in this expansion. And then, so we do this, and then one of these terms is this sort of h sub r. And then next we just expand that part with this randomized methods. So it kind of like alternates. So the final effect is that it alternates between sort of like running through of deterministic terms in some product formula, and then sampling a bunch of times from the random part, and then going on and so forth.
So it's a very basic thing. I'm not sure I understood how you make sure that the coefficients are positive here.
Oh, right. Yeah, that's a fair question. Well, because there are Pauli operators, I can just incorporate the sign into the Pauli operator. Yeah.
Okay, are there some more questions? Okay, then if not, let's thank the speaker again.